I am now live. Let me just check if I'm at 2:14, bro. Hey, hey. All right, all right. Let's spark introduction. Okay. Share my screen. Touch screen. This one. Share audio. Share. I can't believe I'm wasting my time on this. Data engineering. Yes. Spark. Spark. Encode. Just a recap of Spark because. Okay.
Have you ever been training a machine learning model and the training data that you get is bigger than the machine that you have? Or have you ever been running an SQL query and then you realize it's going to take all night to finish? Well, you could just buy a bigger machine and upgrade it, and you could just patiently wait for the SQL query to finish. But what about when the training data grows and grows and grows, and your database starts to go into the millions and millions of rows? A great solution to this is Apache Spark.
Hey, David, sorry to interrupt, man. This is great stuff. I just want to remind everyone at home to like and subscribe. It helps us grow the channel so we can bring you more great videos. Some of
Testing it using some code, and then you have to run it on your hardware, which is where the problem usually arises. Your hardware is not big enough or powerful enough. And finally, you have to store that data. And very often, the data that you come out with is much bigger than the data that you started with. Spark addresses this through its stack. At the very top, we have Spark libraries like Spark SQL, MLlib for machine learning workloads, and Spark R. All these are supported by the Spark Core API. Underneath that, Spark takes the hardware problem, splits it into multiple computers using something like Kubernetes or EC2, and handles all the resource management.
What did
Finally, management using something like Kubernetes or EC2, and handles all the resource management. Finally, Spark has data stores that you can access to store all the data that's generated from your workload. So next time you have a big data problem, spare your wallet and spare your stress levels, use Apache Spark.
Apache Spark architecture. Let's just go to the documentation itself. That's not it. That's not it, bro. That's not it. Although that is good. That is good. First of all, that's a little too much. Okay. Apache Spark core architecture. Let's put this here. Okay. Languages. So before this, what is Spark? Spark is an open source big data parallel processing framework. Spark is a, what is okay. Spark is an open source big data parallel processing framework. I guess that's it. ChatGPT. Give me a one-line definition of Apache Spark. Apache Spark is an open source unified analytical engine for large scale data processing, providing high level supporting general distribution. This is my answer. What the heck? This is my definition of Spark is an open source. Apache Spark is an open source unified. Apache Spark is a Apache Spark is a open source unified big data parallel processing framework. How about this? It is a unified parallel processing framework for analyzing big data. Okay. Now programming language. Okay. Now let's go into the Spark architecture. That's not it. Park architecture. Park. Oh, bro, what is this? Layers of Apache Spark explained. What are the layers in Apache Spark and what do they do? I learned that the layers get word spark spark replay then scheduling slash resource managers. Apache Spark is some servers and each distinct from programming these libraries. The code engine that provides basic functionality like scheduling, core, scheduling, readiness, storage. The various cluster manager that Spark can run, they can handle the allocation and scheduling of resources. What is a cluster manager? This document gives a short overview of how Spark runs on clusters to make it easier to understand them. Read through the application submission guide to learn about launching an application. Names. Spark allocation runs as an independent set of processes on a cluster coordinated by Spark context object in the main. Specifically, to run on a cluster, the Spark context can connect to several types of cluster managers. Spark's own cluster, standalone cluster, which allocates resources, which allocate resources across our application. Once connected, Spark is executed. Cluster manager is the component within the distributed computing environment responsible for managing resources. Efficient distribution of Spark applications by coordinating allocation of resources. A program that that resources above edges, tasks, ability, cluster manager, isolation, and which means Did Spark acquires a gift? There are several useful things to know about this architecture. Okay, okay, there we go. I have a serious problem with this ad thing.
Hello everyone, this is AK. In this week of video, I'm going to explain the Spark architecture, why I took this concept.
Bro,
Hello everyone, this is AK. In this week of video, I'm going to explain the Spark architecture. Why I took this concept means Spark is one of the highly used data processing tool right now. Without Spark, we can't do any major big data processing and transformations. There are a lot of tools out there for big data manipulations. Some of them are like Hadoop, MapReduce, but due to the data evolution, we are forced to look different ways for data processing. Apache Spark is one of the popular data processing framework right now, and people who are in data engineering and data science domain must know this framework while cracking the interviews. There will be a lot of questions could be asked from Apache Spark, but one of the important question is Spark architecture. Apache Spark having its own architecture, there will be high chance of asking the explanations of Spark architecture questions in the interviews. And it is very important and basic parameter to understand the Spark concept. So before that, if you want to receive good quality data videos from me, press the subscribe button to get notified. Let's get started. In this video, we are only focusing on Spark architecture. But if you want to know the other big data tools like Hadoop and MapReduce, then comment it down. I will definitely make a new video of it. Okay. So let me start with the Spark ecosystem so that you can easily understand the Spark framework better. In the first block you are seeing here is a Spark services. Spark provides different services and features like Spark SQL, streaming data handling, machine learning support, and graph computation. And if you are using Spark, you can use these services from Spark to handle the big data computations. And in the next set of blocks, we have the Spark APIs. So we already seen the Spark services, and now you have to know how to communicate with those services. You can interact with Spark through different languages like Scala, Python, Java, R. So this is how the Spark ecosystem works. Let's move to its architecture. Apache Spark follows master and slave architecture. So look at its architecture. SQL, streaming data handling, machine learning support, and graph computation. And if you are using Spark, you can use these services from Spark to handle the big data computations. And in the next set of blocks, we have the Spark. APIs. So we already seen the Spark services, and now you have to know how to communicate with those services. You can interact with Spark through different languages like Scala, Python, Java, R. So this is how the Spark ecosystem works. Let's move to its architecture. Apache Spark follows master and slave architecture. So look at the picture here. The master is the driver program which controls each and every worker node. And the worker nodes are the actual blocks which will do the work assigned by the driver program. Other than these two, we have the cluster manager, which is used for allocation and managing the resources. And in the next set of blocks, we have the Spark. Comment it down. I will definitely make a new video of it. Okay. So let me start with the Spark ecosystem so that you can easily understand the Spark framework better. In the first block you are seeing here is a Spark services. Spark provides different services and features like Spark SQL, streaming data handling, machine learning support, and graph computation. And if you are using Spark, you can use these services from Spark to handle the big data computations. And in the next set of blocks, we have the Spark APIs. So we already seen the Spark services, and now you have to know how to communicate with those services. You can interact with Spark through different languages like Scala, Python, Java, R. So this is how the Spark ecosystem works. Let's move to its architecture. Apache Spark follows master and slave architecture. So look at the picture here. The master is the driver program which controls each and every worker node. And the worker nodes are the actual blocks which will do the work assigned by the driver program. Other than these two, we have the cluster manager, which is used for allocation and managing the resources which are required to run the job. So this is the one-line understanding about the Spark architecture, but these things are not enough to understand its complete workflow. So let's see the workflow. The workflow begins from the driver program. When the Spark program is submitted, the driver program in the master node initializes the Spark context. The Spark context is something that will work with cluster manager. Spark context is used to represent the connection of Spark cluster, and it will use it to create the RDD data structures. Once it is initiated, it converts the Spark program containing code transformations and actions into DAG. DAG is briefly called as Direct Acyclic Graph. It performs a sequence of computations on the data. So how exactly it works? Once the DAG gets created, it divides the data into RDD partitions for the executors. DAG is basically a graph structured layer. The nodes are the partitions of RDD and edges have the transformations. Once it happened, the driver program schedules which task will get executed on the worker nodes. So when the worker allocation is done by the driver program, the cluster manager assigns resources for the task execution. There are different type of cluster managers that are available for the Spark. Some of them like Apache Mesos, Kubernetes, Hadoop Yarn, and standalone scheduler. The standalone scheduler is the default one that comes with Spark installations. The main work of scheduler is to assign the executors on the worker node. The executors keep a task memory on the RAM for the references or recollection purposes. The driver program have the control of the executors. So once the execution gets started, they have two jobs to do. The first job of executors to run the tasks which are assigned by the driver program, and then it has to report those status to the driver program. These are the exact workflow of Apache Spark architecture. I think I explained correctly. If I miss anything or explained incorrectly, please comment it down so everyone can understand it better. Thanks for watching and thank you. See you on next week.
Runtime architecture of Spark application. In this video, I'm going to explain about the runtime architecture of Spark application. By the end of this video, you will know the internal details of how a Spark application runs. Apache Spark uses master-slave architecture. The client submits a Spark user application code. When an application code is submitted, the driver implicitly converts user code containing transformations and actions to logical directed acyclic graph, DAG. At this stage, it also performs optimizations, such as pipelining transformations. Then it converts the logical graph, DAG, into physical execution plan with sets of stages. After converting into physical execution plan, it creates physical execution units called tasks under each stage. Then the tasks are bundled to be sent to the cluster. Now, the driver talks to Cluster Manager and negotiates for resources. Cluster Manager launches executors in worker nodes on behalf of the driver. At this point, the driver will send the tasks to the executors based on data placement. When executors start, they register themselves with the driver, so driver will have complete view of all executors. Executors start executing the tasks assigned by the driver program. At any point of time, when the application is running, driver program will monitor the set of executors that runs. Driver will also schedule future tasks in appropriate location based on data placement. The user program may cache data in certain locations using cache method or persist method. Driver tracks the location of cache data and uses it to schedule future tasks that access that data. Driver exposes information about the running Spark application through a web UI at port 4040. So, if you are running the application in localhost, the web UI link will be http://localhost 4040. When driver's main method exists or when it calls Spark context stopped method, it will terminate the executors and release resources from Cluster Manager. In this video, we saw the runtime architecture of Spark application and how a Spark application runs when a job is submitted. In the next video, we will learn about RDD, which is the Spark's core system.
Let's go to
Runtime architecture. Of Spark application. In this video, I'm going to explain about the runtime architecture of Spark application. By the end of this video, you will know the internal details of how a Spark application runs. Apache Spark uses master-slave architecture. The client
So let's go to Client submits
Client submits a Spark user application code. When an application code is submitted, the driver implicitly converts user code containing transformations and actions to logical directed acyclic graph, DA. At this stage, it also performs optimizations, such as pipelining transformations. Then it converts the logical graph, DAG, into physical execution plan with sets of stages. After converting into physical execution plan, it creates physical execution units called tasks.
Yeah. Hey.
under each physical execution plan with sets of stages. After converting into physical execution plan, it creates also performs optimizations, such as pipelining transformations.
నీ అబ్బా
Then it converts the logical graph, DAG, into physical execution plan with sets of stages. After converting into physical execution, at this stage, it also performs optimizations, such as pipelining transformations. Then it converts the logical graph, DAG, into physical execution plan with sets of stages. After converting into physical execution plan, it creates physical execution units called tasks under each stage. Then the tasks are bundled to be sent to the cluster. Now, the driver talks to Cluster Manager and negotiates for resources. Cluster Manager launches executors in worker nodes on behalf of the driver. At this point, the driver will send the tasks to the executors based on data placement. executors, creates physical execution units called tasks under each stage. Then it converts the logical graph, DAG, into physical execution plan with sets of stages. After converting into physical execution plan, it creates physical execution units called tasks under each stage. Then the tasks are bundled to be sent to the cluster. Now, the driver talks to Cluster Manager and negotiates for resources. Under each stage. Then the tasks are bundled to be sent to the cluster. Now, the driver talks to Cluster Manager and negotiates for resources. Cluster Manager launches executors in worker nodes on behalf of the driver. At this point, the driver will send the task to the executors based on data placement. When executors start, they register themselves with the driver, so driver will have complete view of all executors based on data placement. When executors start, they register themselves with the driver, so driver will have complete view of all executors. Executors start executing the tasks assigned by the driver program. At any point of time, when the application is running, driver program will monitor the set of executors that runs. Driver will also schedule future tasks in appropriate location based on data placement. The user program may cache data in certain locations using cache method or persist method. Driver tracks the location of cache data and uses it to schedule future tasks that access that data. Driver exposes information about the running Spark application through a web UI at port 4040. So, if you are running the application in localhost, the web UI link will be from Cluster Manager.
Yeah, I think we're good. Spark theory. Let me just quickly explain so it makes sense. So Spark is a open source parallel processing big data analytical framework. This, as you can see on the screen, that is the as you can see on the screen, that's the different layers of Spark. Okay, so you can interact with the Spark core, which is the main engine of the um, Spark, which is the main engine of Spark. You can interact to the core with your programming languages, and then there are certain APIs also, and then this one's the cluster manager, and then this is the storage. So excuse me, those are some layers. However, this is the actual structure of the Spark. So let me just bring this over here. So this is the architecture of Spark. Um, so this is the architecture of Spark. So Spark is basically, how do you say that? This is the architecture of Spark, and Spark uses master-slave architecture, where the master is the driver node or the master node, and the worker nodes are the slaves. So when the client passes the user application to the driver node, when the client passes the application to the Spark cluster, it goes to the driver node, where the driver node converts that user application into a directed acyclic graph. here here is where the transformations and actions are optimized, and there's an execution plan that is created, which is the next step. Um, so this is a physical execution plan that is the following step of the tag creation. After the tag creation, um, so there are the user application is the user application is divided into stages, which is further divided into tasks, and these tasks are the fundamental unit of um, the the most granular level of the user application is called a task, and this task is executed by executors, or it is executed in the worker node. So the driver node negotiates with the resource manager in order to get resources to execute these tasks, and the resource manager provides these resources, and then the tasks are executed. Connections are established to the driver node in order for the driver node to monitor the executors. But I have a question though. First, and I need to speak up, bro. It's crazy. Chat G, Chat GPT, Chat GPT, Chat GPT. A task, the most granular level of a user application submitted by the client to. Probably the question that I just asked is it's the vector embedding of that question is crazy, and ChatGPT doesn't know what to do. I'm still waiting on the answer. What's up? Hey, what's up? Hey, what's up? 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 But this is crazy. This is unacceptable. Reload the thing. In Apache, the term task is indeed often considered the most granular level of execution within the Spark job. Oh shit, Spark job. Oh my god. I don't know what a Spark job is. Application? Job? Damn. Bruh. Okay. Levels of execution in Apache Spark. Oh my god. Levels of execution in Apache Spark. Levels in Apache Spark. Uncle Amayo. Uncle Ayayo. So first comes highest level and represents the user program that is subject to the Spark cluster. So there's application is so there's application. It consists of users code and the configurations. Highest level user program uh, uh, contains code and cluster. Highest level program. Highest level program submitted cloud cluster contains code and cluster configurations. Job on action. Jobs. Okay. Actions create jobs. Since we said that. Because the creation of job is job is a set of parallel computation spark. Job is a set of parallel computations. Each jobs are divided into periods. A stage corresponds to set of tasks that can be executed. Jobs are divided into stages. Each is stage corresponds to a set of executed. Stages are separated by occasions. Data shuffle. Task is the smallest unit of work in Spark. Okay. Unit of work in Spark. Each stage is divided into tasks. Stages are divided into tasks. Just so so there's an application, then application there is job, and job there's a stage, there is a application, user application, job, page, then entry point into entry point for using uh, cluster configurations. This is Spark architecture. Okay, is that all? Oh, Spark engine, bro. Come on, bro. engine. Full engine. Yeah, it doesn't say. Spark architecture. Architecture. Done. Spark architecture. Cluster configuration. Yeah, okay. Then in that case, I think we are good with Spark architecture. What else is there to learn about Spark architecture? Okay, I'm just going to start the Udemy course then. Hey, Udemy!
Welcome back. By now, you already have background in distributed computing and have seen the data lake as a modern data platform. I also mentioned that Apache Spark is the most popular and widely adopted data processing framework in a data lake. So in this lecture, I'll take you a little deeper into Apache Spark and help you understand Spark as a unified data analytics and processing platform. Let's start with a simple question. What is Apache Spark? Let me Google this question. You will see two references. The first one is for the Apache Spark homepage. Let me check it. What do you see? You will see a definition here. This definition doesn't tell much. Let's look at the Databricks website. They are the main driving force behind the Spark. You will see a similar thing here as well. Scroll down and you will also see a diagram. So let's start with this diagram. Apache Spark is a distributed data processing framework, and this diagram represents the Spark ecosystem. This figure will help us understand how the whole ecosystem is stitched together. So the Spark ecosystem is designed in two layers. The bottom layer is the Spark core layer. Then we have the next layer as a set of DSLs, libraries, and APIs. These two things together make the Spark ecosystem. The Spark core layer itself has got two parts: a distributed computing engine and a set of core APIs. And this whole thing runs on a cluster of computers to offer you distributed data processing. However, Spark does not manage the cluster. It only gives you a data processing framework. So you are going to need a cluster manager. People use different names for cluster manager, such as resource manager or the container orchestrator. However, they all offer similar services to Spark, and Spark is designed to work with both. Spark was initially based on Hadoop MapReduce, and it was adopted in the Hadoop platform. So the Hadoop Yarn Resource Manager is the most commonly used cluster manager for Spark. However, you have other options, such as Mesos and Spark standalone cluster manager. The newer versions of Spark are also compatible with Kubernetes as a cluster orchestrator. Similarly, Spark also doesn't come with an inbuilt storage system, and it allows you to process the data which is stored in a variety of storage systems. The most popular and commonly used storage systems are HDFS, Amazon S3, Azure Data Lake Storage, Google Cloud Storage, and the Cassandra file system. So one thing is obvious: Apache Spark does not offer cluster management and storage management. All you can do with Apache Spark is to run your data processing workload, and that part is managed by the Spark Compute Engine. So the Compute Engine is responsible for a bunch of things. For example, breaking your data processing work into smaller tasks, scheduling those tasks on the cluster for parallel execution, providing data to these tasks, managing and monitoring those tasks, provide you fault tolerance when a job fails. And to do all these, the core engine is also responsible for interacting with the cluster manager and the data storage manager. So the Spark Compute Engine is the core that runs and manages your data processing work and provides you with the seamless experience. All you need to do is submit your data processing jobs to Spark, and the Spark core will take care of everything else. Now let's move a level up. The second part of the Spark core, the core APIs. This layer is the programming interface layer that offers you the core APIs in 4 major languages: Scala, Java, Python, and R programming language. These are the APIs that we use to write data processing logic during the initial days of Apache Spark. However, these APIs were based on resilient distributed datasets, RDDs. And people found them a little tricky to learn and use for their day-to-day data processing work. Some people still use them today. However, these APIs are the most complicated way to work with Apache Spark. They also lack some performance optimization features, and the Spark creators are now recommending to avoid them as much as possible. However, these APIs can offer you the highest level of flexibility to solve some complex data processing problems. The topmost layer is the prime area of interest for most Spark developers and data scientists. This layer is again a set of libraries, packages, APIs, and DSL. These are developed by the Spark community over and above the core APIs. So you will be using these top-level APIs and DSLs. But internally, all of those will be using Spark core APIs, and ultimately, things will go to the Spark Compute Engine. The topmost API layer is grouped into 4 categories to support 4 different data processing requirements. However, this is just a logical grouping, and there is no rigid boundary. Things are going to overlap in most of the real-life projects. The first group is a set of 2 things: Spark SQL and then Spark Data Frame or Dataset APIs. Spark SQL allows you to use SQL queries to process your data. So that part is quite simple for those who already know SQL. Spark Data Frame will allow you to use functional programming techniques to solve your data crunching problems. These APIs are available in Java, Scala, and Python. Both of these together can help you solve most of the structured and semi-structured data crunching problems. The next one is Spark Streaming Libraries, and they allow you to process a continuous and unbounded stream of data. Then you have a set of libraries specifically designed to meet your machine learning, deep learning, and AI requirements. The last collection is for graph processing libraries, and they allow you to implement graph processing algorithms using Apache Spark. So the topmost layer is nothing but a set of libraries and DSLs to help you solve your data crunching problems. And all these are available in multiple languages, such as Java, Scala, Python, and R. The next obvious question is this: what is so great about the Spark ecosystem? Why is it so popular? At a high level, there are 3 main reasons. Spark will abstract away that you are coding to execute your program on a cluster of computers. In the best case scenario, you will work with tables and use SQL queries. You will feel like working with a database. In the worst case scenario, you will be working with RDDs or data frames. You will feel like working with Java or Scala collections or Python data frame. That's it. Everything else, all the complexities of distributed storage, computation, and parallel programming is abstracted away by the Spark core. Spark combines the capability of SQL queries, batch processing, stream processing, structured and semi-structured data handling, graph processing, machine learning, and deep learning. All of this in a single framework using your favorite programming language. You can mix and match them to solve many sophisticated requirements. Compare it with old Hadoop and MapReduce code. Spark code is much shorter, simpler, and easy to read and understand. You also have a growing and evolving ecosystem to offer ready-to-use libraries, algorithms, and integrations with a wide variety of other systems. And these three things make Spark a super popular distributed computing platform for data processing. That's all about Spark. Now let's talk about Databricks. Apache Spark is an open source project. The original creators of Apache Spark donated it to Apache Foundation and made it an open source project. However, that same team formed a company and a commercial product around the Apache Spark. The company and the product are both named Databricks. So what do they offer over and above the Apache Spark? Databricks brings Apache Spark to the cloud platform. In fact, Databricks product is known as Databricks Cloud. And the Databricks Cloud is only available on the cloud platforms, but they are available on AWS, Azure, and Google Cloud. So Databricks brings Apache Spark on all the major cloud platforms. Databricks allows you to launch a cluster for running Spark applications automatically. That takes a lot of burden from you. You do not need to configure and launch a cluster manually for running your Spark applications. Databricks allows you to start, configure, and install all the dependency and runtime libraries on all the nodes to your Spark application. And you can do that using just a few clicks. So in a nutshell, Databricks offers you an easy way to configure, launch, and shut down the clusters in the cloud environment. Databricks Clouds also offer you notebooks and workspace for Spark development. These workspace and notebooks are as good as IDE for Spark development. You can use the notebooks to develop, share, and collaborate with your colleagues for Spark development. You can also integrate Databricks notebooks with configuration management tools such as Git. Databricks Cloud also provides you administration control, so you can manage access for your workspace, clusters, and storage, and implement security controls. Databricks offers you an optimized and tuned version of Spark over and above the Apache Spark. Databricks Spark runtime is 5 times faster than the standard Apache Spark runtime. Databricks also offers you an integrated Hive metastore to store metadata, allowing you to create databases, tables, and views using Spark SQL. On top of this, Databricks also offers you an advanced SQL query engine called Photon, which allows you to gain data warehouse-grade performance of your SQL queries and dashboards on top of the data lake infrastructure. Databricks Cloud offers seamless data lake integration that offers ACID transactions and data consistency features to your application workload and Spark SQL. Databricks also offers MLflow, which allows us to manage the machine learning lifecycle, including experimentation, deployment, model registry, etc. That's not all. Databricks is also offering some industry-specific solution accelerators for rapid adoption and solving common industry-specific problems. Great. So Apache Spark is at the core, but Databricks has a... Welcome back. In this section of the course, I'll discuss the following things. This course is full of examples, exercises, and micro projects. You will need to set up your Spark development environment for doing your hands-on activities and project work. Spark development happens in two kinds of environments, in cloud platform and on your local machine. So we will learn to set up both kinds of environments. I'll explain Spark development environments and when to use what. Then I'll help you set up a cloud development environment and help you become familiar with the cloud environment. We will also create a simple... Welcome back. We'll learn to set up a Spark development environment. I showed you a Spark example to give you the following feel. What do we do in Spark application? How does a typical Spark application code looks? And how to write and execute your Spark application? Apache Spark is a data processing engine. So in a typical Spark application, we read data from a source, process it, and write or present the results. And this course is all about learning how to do these three things: read, process, and write. I also showed you a sample code of the Spark application. You learned how to write and execute Spark code. Now it's time to start learning Spark programming and develop your Spark coding skills. We will take a project-driven approach to learning things. So I'll define a micro project and give you some requirements. Then we will learn to build a solution for the given project problem. Along the way, I'll explain various concepts and techniques of Spark programming. So let me start with the micro project problem statement. I'm giving you the fire calls for service dataset. Here are the details of the given dataset. This dataset represents a response to calls at fire units. Scroll down and you will see the column names. So we have 34 columns in this dataset. You can also see a preview of the dataset. Scroll down to the bottom of the page and click the terms of use. This dataset is available under the PDDL terms. Click this PDDL link in the side panel. You will see the Open Data Commons URL. Copy the URL and paste it into a new browser tab. Scroll down and you will see a plain language summary. Click that. Here we are. So you are free to share, create, and adapt this dataset. Make sense? Great. It is essential to check the terms of use for any dataset that you are using for your learning and experiments. I showed you how to check the license terms of this dataset. However, we might be using many other datasets in this course. I'll give you references to the data source to check the terms of use yourself, but I would have already checked it once for no licensing restrictions. Make sense? Great. So you are given a San Francisco fire call response dataset, and you are asked to do the following. Load the given data file and create a Spark data frame. Use the Spark data frame to answer the following questions. Basically, we want to do only two things: load the data into a Spark data frame and query it to find the answer to the 10 questions. This whole exercise is to learn two things: how to load data into Spark and how to query data in Spark. We have two approaches to do it, using Spark SQL and using Spark Data Frame API. We will learn both approaches. I'll not teach you SQL because I assume you already know SQL, and that's not the focus of this course. This course focuses on everything else that Spark offers other than SQL syntax. I'll help you learn the Spark SQL approach to solving problems so you can apply your SQL skills to working with Spark. However, the main focus will remain on the Spark Data Frame APIs and other techniques. Make sense? Great. So we want to load the data into a Spark Data Frame and query it to find answers to the 10 given questions. While working on the solution, you will learn the following. Using Spark SQL and DDL statements, Spark Data Frame and Data Frame Reader API, working with CSV files, data frame transformations and actions, how to read a Spark API documentation. It is a small list, but it is a lot to learn. But nothing to worry about. We will start learning things from the following video. See you again. Keep learning and keep growing. Welcome back. In this video, I'll talk about Spark Data Frames. So let's start. We learned that Spark is a data processing platform, right? What other data processing platform do you know? Databases, right? Databases are the most popular and the most widely used data processing platforms. And what do they offer? They offer two things at high level, tables and SQL. A database table allows you to load the data in the table. And the data in a table is internally stored as a DBF file. And these DBF files are stored on the disk. But you don't care about the DBF file and the storage layer. You only care about the table, right? You always look at the table and query the table, right? But what is a table? A table contains two things, table schema and table data. What is a table schema? Simple. It is a list of column names and data types, right? The schema information is stored in a database data dictionary or a metadata store. This is how a table is organized. We have three layers to form a table. The storage layer stores the table data in a file. Metadata layer stores the table schema and other important information. The logical layer presents you with a database table, and you can execute SQL queries on the logical table. Make sense? Great. Now let's see how SQL executes. When you submit a SQL query to your database SQL engine, the database will refer to the metadata store for parsing your SQL queries. And the database will throw a syntax error or an analysis error if you are using a column name in your SQL that does not exist in the metadata store. Here is an example of SQL. The SQL will return an analysis exception because the column XYZ does not exist in the table. So the schema is essential for database table and for the SQL expressions to work correctly, right? The table data is stored in the DBF files behind the table. So if your SQL query is correct and passes all the schema validation, you will see query results. The database will read data from the DBF file, process it according to your SQL query, and show you the results. Make sense? That is all about the data processing in databases. Now let's try database analogy with Apache Spark. Apache Spark offers you two ways of data processing, Spark Database and SQL. Then Spark Data Frame and Data Frame API. The first approach is precisely the same as a typical database. So you will create table and load data into the table. Spark table data is internally stored in a data file. But these files are not DBF files. Spark gives you the flexibility to choose the file format and supports many file formats such as the following: CSV, JSON, Parquet, Avro, XML, and many more. And that is the reason Spark supports structured, semi-structured, and unstructured data. The DBF file format and database engine were designed to support structured data, but Spark is designed to support a variety of file formats, and hence you can store and process a variety of data formats. Make sense? The Spark storage layer also supports distributed storage such as HDFS and cloud storage such as Amazon S3 and Azure ADLS. So you are not limited to disk storage capacity. You can use distributed storage and store large data files. Make sense? Great. Spark also has a metadata store for storing table schema information. So that part is similar to the database. Then Spark also comes with a SQL query engine and supports standard SQL syntax for processing and querying data from Spark tables. However, Spark goes beyond the tables and SQL to offer Spark Data Frame and Data Frame API. So what is a Spark Data Frame? It is the same as the table without a metadata store. What does it mean? Simple. Spark Data Frame is structurally the same as the table. However, it does not store any schema information in the metadata store. Instead, we have a runtime metadata catalog to store the data frame schema information. The catalog is similar to the metadata store, but Spark will create it at the runtime to store schema information in the catalog. This catalog is only valid until your application is running. Spark will delete this catalog when your Spark application terminates. What is the benefit? Why not store the data frame schema in the metadata store? Why create a runtime metadata catalog? Well, we have two reasons for this. Spark Data Frame is a runtime object, and Spark Data Frame supports schema on read. What does it mean? Simple. You can create a Spark Data Frame at runtime and keep it in memory until your program terminates. Once your program terminates, your data frame is gone. It is an in-memory object. Spark tables are permanent. Once created, you will have a table forever. You can drop a table and remove it, but it remains in the system until you drop the table. However, Spark Data Frame is a runtime and temporary object which lives in the Spark memory and goes away when the application terminates. So the metadata is also stored in the temporary metadata catalog. Make sense? Great. The second reason is due to the schema on read feature. Spark Data Frame is designed to support the idea of schema on read. What does it mean? Data frame does not have a fixed and predefined schema stored in the metadata store. Instead, we define the schema when we want to read the data from a file and load it into the data frame. So the difference is straightforward. We define a schema for the table when creating a table. Then we load data into the table. The data must comply with the table schema or you will get an error. However, data frame is different. We load the data into a data frame and tell the schema when loading the data. And Spark will read the file, apply the schema at the time of reading, create the data frame using the schema, and load the data. So a data frame is always loaded with some data, whereas table can be empty. Make sense? You will see all this happening when we start coding. So do not worry much if you do not get the idea of schema on read. I'll show you that with an example. Great. That's all about table versus data frame. You can use SQL on the table. However, data frame does not support SQL expressions. You must use data frame API to process data from a data frame. Since the table and data frame are structurally the same, you can convert them to each other. I mean, you can convert a table into a data frame and vice versa. The point is straight. You have two ways of processing data in Spark, SQL and data frame API. And you can use both at your convenience. You can create a table and use SQL, or convert a table into a data frame and use data frame API on the same table. We will learn all that, nothing to worry about. But for now, we learned some basics about Spark tables and data frames. I hope you understand both of these objects. Let me quickly summarize the difference. Tables store schema information in the metadata store. Data frame stores schema information in runtime catalog. Table and metadata stores are persistent objects, and they are visible across applications. Data frame and catalog are runtime objects and live only during the application runtime. We create tables with a predefined table schema. Data frame supports schema on read. Table supports SQL expressions and does not support API. Data frame offers APIs and does not support SQL expressions. A Spark table and a data frame are convertible objects. So you can convert a table into data frame and save a data frame as a Spark table. And that is all for this lecture. In the following video, we will do some hands-on activities to implement Spark tables and data frames. We will learn to use both, so you clearly understand these concepts. See you again. Keep learning and keep growing. Welcome back. We learned about theoretical concepts about Spark data frames. Now it's time to see it in action. So let me start. I gave you a requirement for creating a data frame using the San Francisco Fire Call Response dataset. The dataset is already available in the Databricks Community Cloud, and it is made available for you by the Databricks for learning purposes. You can access it from the following location in your Databricks Community Cloud. So we do not need to download the data from the source and bring it to the cloud. That part is already done for you. So let me start creating a data frame using the given data file. Start to Databricks Workspace. Here we are. Working in Databricks Workspace requires a Spark cluster. So let me go to the Compute menu and create a new cluster. Hit the Create Cluster button. Give a name to your cluster and create it. Your cluster will start in a few minutes, and Databricks will terminate it if your cluster is idle for 2 hours. Once terminated, you cannot start it again. So if you want to work the next day, you should delete the older terminated cluster and create a new one. You can use your cluster for as long as you want and delete it.
Okay, I think that's about it. I think this is enough of theory, and I'm going to go do some practicals, and I don't think I want to stream my practicals. So that's cool. Thank you for joining today. Bye bye.